finish that off. So what we need to do is we need to rewrite the denominator of the second term, which I'll go ahead and do this separately. So we have x squared plus 6x plus 22. So this is, you take half of 6, which is 3, and you square it, and so you'll get 9. So to make this work out as a complete square, we're going to add 9, and hence, as a consequence, we're also going to subtract 9. Now this can be then rewritten as a perfect square, which is going to be x plus 3 quantity squared. And then we do the math here, which is 21 minus 9 is 13. So get plus 13. So now what we can do is let's go ahead and factor out the half. So we're coming back here just to finish this off. So we got a half times the integral of 2x plus 6 divided by x squared plus 6x plus 22 dx. And then the second integral we can write as 2. So I'm going to factor out the constant. 2 times the integral of 1 divided by 13 plus x squared plus 3 quantity squared dx. And at this point, we can use two different u substitutions. So for this one, u is going to be the entire denominator. And over here, u is going to be equal to x plus 3, and a is going to be equal to the square root of 13. That's because u squared is equal to x plus 3 squared, and a squared equals 13. And the last thing we have to do, well, we have to find du for both cases. So du here is 2x plus 6, which matches that exactly. And down here, du is just equal to dx, because the derivative. The only time you don't get du equals dx is if you had something like 2x plus 3, quantity squared. So if this is not just x, then du does not equal dx. It would be du would be equal to some constant times dx. So with those substitutions, we can rewrite the first integral as the integral of 1 over u du. So this part here, and I forgot dx, so I do that sometimes too, but usually I catch myself. So hold on just a second, I've got to turn my speaker off. So yeah, anyway, this 2x plus 6 times dx is du. This is u. And then the second part is going to be 2 times the integral of 1 over a squared plus u squared du. Now, is it kosher for me to use different u's? I mean, as long as you know what you're doing and you keep everything straight, I think it's okay. It's just it's so easy. I get so used to using u that if I use anything other than u, it bothers me. So if you wanted to, you could probably call this w, and you'd have a plus w squared. But as long as you don't have a problem with it, I don't have a problem with it. Okay, so now, again, the whole goal is to get to a point where these integrals are something that we can look up in the tables in the book, and those are in the tables. So to go from here to here, we just use our sheet. So the integral of 1 over u du is the natural log of the absolute value of u, and the integral of 1 over a squared plus u squared is equal to 1 over a times the arc tangent of u over a, and we just add one arbitrary constant because there's an arbitrary constant from this one and one from this, but two arbitrary constants added together results in one arbitrary constant. And then finally, you go plug back in what you've chosen to be u. So this one's going to be 1/2 the natural log of the absolute value of x squared plus 6x plus 22. And here we'll have 2 divided by the square root of 13 times the arc tangent of u, which is x plus 3, divided by the square root of 13 plus c. which if you finish there, that's fine. The only thing we might change is just multiply and divide by the square root of 13. So if we do that, we'll get 2 times the square root of 13 over 13 times the arc tangent of the square root of 13 times x plus 3 over 13 plus c. Now I've made the test up. I looked at what I did last year and just changed the problems, but the same material. And I don't have one of these on the last test. I do have one of these on the final. So you still got to. So if you don't quite understand this 100%, you're okay for the test. But by the time you get to the final, there'll definitely be one of these on the test. Okay. Before we, I've got a handout to do some extra problems because that's pretty much it. That's the end of the material for this semester. All we're going to do now is just practice what we know, hopefully what we know. But this is actually back to the inverse trig functions. So let's say I have the arc sine of the sine of a half. Does anybody know what the answer is? It's an easy answer. Yeah, it's 1/2. Okay. Why is that? Because it's saying what angle has a sine whose sine is a half. It's also, you're doing the inverse. You have two functions that are inverses of each other. So remember we said the arc sine of the sine of x equals x. So in this case, x is a half. Another way you can think about it is, if I did it the other way, the sine, and actually this is actually I probably would, it might have been made more sense if I used something like pi over 2 or something, or pi over 3. Let's do that. So pi over 3. So the sine of the angle pi over 3 is some value, and the angle whose sine is that value is the original angle that we talked about. The other way would be to do the sine of the arc sine of a half, say. So the sine of the angle whose sine is a half is a half. So those are easy. If you have the function and the inverse function and you have the composite function of those two, the answer is always whatever you start off with. The question is, what is let's say the arc tangent of, well, let's do the other way first. Let's do the tangent of, so let's say we have the tangent of the arc sine of a half equals question mark. So the first part is saying what is the angle whose sine is a half. So here's theta. So theta equals the angle whose sine is a half. So if the sine is a half, then the opposite side length is 1 and the hypotenuse side length is 2, and by the Pythagorean theorem the length of the adjacent side is the square root of 3 over 2. No, it's not. It's what is it? Let's just figure it out. It's going to be 4 minus, so it's going to be the square root of 3. Okay. So using this interior part, when I say the angle whose sine is a half is theta, I define this as theta, so the opposite side is 1, the hypotenuse is 2, and that's what I'm doing. But then I use the Pythagorean theorem to find out what the third side is. So if I say, what is the tangent of the arc sine of a half is, then what you do is you just go back to this triangle. It's basically saying what is the tangent of theta. Well, the tangent is going to be equal to the opposite over the over the adjacent, which turns out to be the square root of 3 over 3. So the tangent of the arc sine of a half is the square root of 3 over 3. And that's because the arc, the angle, the actual angle whose sine, we didn't actually, in this case, I don't even know what theta is. When I do the composite thing, what I'm doing here is I'm just setting up the ratios of the different sides of the right triangle. So what this allows me to do is to define these two sides of the right triangle, which then allows me to use the Pythagorean theorem. And then to answer the second part of the question, then I just use those lengths with the appropriate trig definition to come up with the answer. Now, if you wanted to figure out the angle in between, the way you would do it is you would say, theta equals the arc sine of a half. And the angle whose sine is a half is pi over 6. And then the second part is asking you what is the tangent of pi over 6. And the answer is the square root of 3 over 3. Okay, so that, in this case, I've actually figured out the angle. But over here, I never had to figure out the angle. I could do it just by looking at the different sides of the triangle. Nowhere did I say, using this, that theta was some pi over 6. But here I did, and you get the same answer, obviously. Okay. Now the question also is there another angle? Is there another angle that this works for? And not really, because the arc sine is based upon limiting the domain of the sine function from negative pi over 2 to positive pi over 2. So am I doing that the right way, or am I doing it the wrong way? Is it from negative 1 to 1? Yeah, when you define the arc sine, you're limiting the sine from negative pi over 2 to positive pi over 2. So there's only one solution to this answer. There's not more than one solution. Now I could do the same thing with a half. If I had what is the tangent of the arc sine of negative 1/2, which doesn't actually fit a triangle exactly because you have a negative sign in there. So it's, it doesn't, you can't always use the triangle. You can use the triangle to define the lengths of the sides, but you might have to think a little bit more if you're dealing with something that's not in the first quadrant. So let me just give you another example. So if I said, what is the sine of the arc tangent of 4? I'll do one more for you and then I'll let you do it. So what you do here is you would draw the right triangle. You'd say this is theta. And the tangent is the length of the opposite side over the adjacent side. And therefore, the hypotenuse is going to be 17. This squared plus that squared, square root. So then when you take the sine of theta, in this case, the sine of theta, where theta equals the angle whose tangent is 4, the sine of theta is going to be equal to 4 divided by the square root of 17. Okay, so that's your second example. So I'll make a third example up here. Let's say, what is the sine of the sine of the arc? That's just the one I gave you, so I need to do something different here. That's too easy. Okay, let's say, what is the cosine of the arc cotangent of 3? Okay. So give that one a try. Remember, cotangent is adjacent over opposite. So you use that inside information to define two sides of your triangle. In this case, the opposite, or the adjacent to the opposite. Then you'll figure out what the hypotenuse is. And then you use the definition of the cosine to come up with the answer. So I think that's the right answer. So we define this as theta. The cotangent is adjacent over opposite. 3 squared plus 1 squared is 10. Square root of 10 is the hypotenuse. The cosine is the adjacent over the hypotenuse. And then you work that out. Okay. Will you actually have to use that in any of our calculus problems? Probably not, but I just thought I would cover that. This one you'll actually will need to know how to do. So if I said, if I ended up with a definite integral where I had to evaluate, let's say the definite integral result was 1/2 times the arc sine of x between 1/4 and 3/4. Okay, so get your calculators out and tell me what the answer is. So what you're doing here, of course, is you've got a definite integral. So all you're going to do is you're going to plug in 3/4 and then subtract plugging in 1/4. So it's just plugging stuff into your calculator. You'll have to do this on your test, so make sure everybody knows what they're doing. So Mark, you got an answer for me yet? Okay. What did Mark do wrong? It's not 17. Did anybody get something different? Michaela, what'd you get? You got an answer yet? 0.13. Let's see what I got. I got 0.2976. Anybody get that? Okay. So I'm not sure what. See if you can figure out where you went wrong. Talk to your neighbor if you need some. If they got the right answer, they can show you. But basically, you take 0.5 times, and you have a left parenthesis, the inverse sine of 0.75 minus the inverse sine of 0.25. They're always going to be in radians. That's where Mark went wrong. He didn't change it to degrees, so make sure it's in radians. If you get, usually the numbers that when you have radians are going to be on the order of, a fraction of something. They're not going to be 20 something. So that's, you might write yourself a note on your cheat sheet. right, like at the top, because you're not going to have to do anything in degrees. So just make sure you change your calculator to radians. Okay, so that was the purpose of that one, just to see if you had it in radians instead of degrees. Now, the second, so that's one possibility, because we have three integrals. This is the integral of 1 over the square root of a squared minus u squared. The other one, let's do another one here just to make sure everybody's. So let's say we have 0.7 times the arc tangent and of x evaluated between 7 and 3. So the arctangent allows us to have a much wider range of x values. So again, that should not be very difficult. It's 0.7 times the arctangent. Obviously, your calculator has the other form of, and if you'd like to use tangent to the -1 power, that's fine. I'm not sure why I chose. Sometimes I do one and sometimes I do the other, but okay. So let's. I'm going to call on somebody once I get an answer, so I know what the answer is. Okay, Jacob, you got an answer for me? 0.1259. Sounds like a good answer. Okay. So the answer is 0.1259. Okay, so remember, this is the result from the integral of 1 over a squared plus u squared, or x squared. Now let's try this. Let's try 21 times the arc secant of x evaluated between 4 and 10. So just use your arc secant button on your calculator. You're like, there is no arc secant button, right? Okay, this is the whole purpose, because there's a problem on the test where you have to evaluate the arc secant. Okay, and most people they don't. You do mostly sine, cosine, and tangent. It's very rarely that you do secant. So So what we have to do here is we have to 21 times the arc secant of 10 minus the arc secant of 4. Does anybody know how to rewrite that in terms of the arc cosine? Which we do know how to do on our calculator. So what do you think I should do here? Yeah, so it's just, you just take the reciprocal of whatever you're evaluating. So it's the arc secant of 10 is the same as the arc secant, arc cosine of 10. That makes sense because secant is hypotenuse over adjacent. Cosine is adjacent over hypotenuse. So when you have that on your test, and you're only going to end up with arc secant because we only have the three integrals where we get the arc sine, the arc tangent, and the arc secant. And the arc tangent and sine you just plug into your calculator, just make sure it's in radians. So go ahead and do that. And it's true for all of the arc cosecant is 1. You take the sine of 1 over x instead of the arc cosecant of x. And I get, well, let me see what you get. Seth, what'd you get? 3.2. Yep. Okay, so everybody's ready for that problem now. Okay, let me hand this out. We're going to do some selected problems today and maybe some more on Friday. Also, tomorrow, or the Thursday, do not use your calculators to confirm your answers, okay? So I just confirm your answers by working the problem again. Okay, so don't use the integration feature. And the question is, I wondered whether mine has it. Can anybody look at my calculator and tell me whether it does that? Evan. Or is it the ones you guys have? Because I didn't even know it did that. Does it? Math.
Math. You have it as like a function where you input like arguments.
Yeah.
Whereas ours has it like fancy.
Oh, so yours is easier to do than mine is. Okay. Yeah. So you function integrate. So does that give you a function, or does that just give you a value?
I feel like it would, because it doesn't have like a computer algebra system on it, does it? It says only a TI-84. So
Yeah.
it should be able to do like antiderivatives.
Does it?
But I don't know how you would put in the arguments.
Yeah, no, I don't know.
I feel like it would probably be like lower bound, upper bound, function, and then like
Yeah.
variable of integration.
Yeah, I'll have to look that up. I mean, it seemed like yours does more than mine does. Okay, so we're actually going to skip over some of these. We'll just talk about, the first page, when you have the derivative of the arcsine, the arctangent, and the arcsecant, you basically just use the chain rule, and so, so just use the chain rule. Okay, that's all you do. You have the formula. So those are real easy. There is one of those on the prop test, so it always looks kind of strange because you end up with the argument. It's like 1 over the square root of 1 minus u squared, and u is some weird, it's not just x, so it ends up looking a little funny. So let's go to the back of the first page. There we have just the 3 different kinds of integrals. So the first one is would be an arcsine because you have the square root of something minus the variable squared, or the variable term squared. The first 2 would be pretty straightforward. The second one is, you'd have the square root of 34 would be a. So a doesn't always have to be a perfect square, and it's not in the test problem. So the last problem, you've got 4x squared, so u would be 2x, and u squared would be 4x squared. But that fits the... Let's go ahead and do the last one. We haven't done that many arcsecant things. So I told you one of those was going to be on the test. So actually all 3 of them. There's going to be an arcsine, there's going to be an arctangent, there's going to be an arcsecant. So we're looking at this one. So when you see, and actually, that should be plus or minus? That should be minus, right? That's wrong. So let's fix that. The secant is should be minus. I think I brought my book today. No, I didn't. Okay. So let me tell you, the formula says that the integral of 1 over u times the square root of u squared minus a squared du is equal to 1 over a times the arc secant of the absolute value of u divided by a plus c. Pretty sure that's right. Does anybody have their integration sheet just to confirm that I've done that correctly? Your formula sheet. Anybody got one of those? So don't forget to bring those on Thursday. I'll bring a few extra copies, but I'd rather, oh, there it is. Okay, so du divided by u times the square root of u squared minus a squared equals 1 over a arc secant. Yep, so that's right. It's in some ways this is kind of like the second kind of u substitution. Not exactly, but you know what we're going to choose u based on this term. U squared is this, and a squared is that. To actually substitute for x here, we're going to have to take our expression for u and solve for x and then plug it in so that we can get the whole thing in terms of u. So give that a try. So like I said, you're going to, anytime you have x times the square root of x, something squared minus something, it's obviously going to be the arc secant. So we're going to let u squared equal u. It's down here. So u squared equals 4x squared. A squared is equal to 16. So give it a shot. Then we'll work through it.
Did you change it to minus 16?
Yeah, I did. I had to change it to minus 16. Did I change it there? Yeah, I did. So I have to tell you a funny story while you're doing your problem. So I came home yesterday. Martha met me at the door, which she does sometimes. It's kind of weird though. Like, why is she coming out? I said, "Oh, do you miss me today?" You know, now that she's retired, you know. So she goes, "I hope you're not mad at me." I go, "Oh." So make a long story short, and she did this. She's done this twice. I guess if this is the worst thing she's done, I'm okay. But Martha likes clean. She's neat, right? She's a neat person. You've had her, and very organized. So a Kirby vacuum cleaner salesman came by, and she bought the vacuum, and she did that like 20 years ago. She bought an Electrolux. That was salesman came by. She can't handle vacuum salesmen. It's just they she has this thing for vacuum salesmen. I don't know what it is. They always convince her how dirty her house is. She's like, "Did you see? Let me show you this. This was we'd already vacuumed this, and this is it's all this dirt." Oh, and I'm like, "Oh God." I'm not saying anything. I'm just okay. That's fine. I'm not. You know, it's your hang up. So, at least, I don't know what else. It's not like fur coats or real expensive clothes. It's vacuum cleaners. Of course, I'm used to my vacuum cleaner, and these didn't do what my vacuum cleaner does. It's not that it's my vacuum cleaner, but when while she worked as teaching the gifted program, I would vacuum every Saturday morning. So that was my job for the last 14 years, was vacuuming. Now that she's retired, she's doing the vacuuming because she's home. But but I had, certain things. She likes to use one attachment to do the floor. It's like this little round thing. And I'm thinking that's very inefficient. You do, 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 do. I like the one that's big and wide, and you just do it on the carpet and on the hardwood floors. And and so my first thought was, what kind of attachment do we have here? Is it going to be as good as the other one? And it wasn't. I'm like, oh, you just spent all that money in a vacuum cleaner, and it's not going to do. So I tried not to be too negative. Don't want to cause sadness because of vacuum cleaner. The thrills of the married life. That's what you're doing. So when you the things you have to do here is if this is u squared, then u is 2x. If this is a squared, then this is a. So you take the derivative of u and you get du is equal to 2 dx. Also, because I have x by itself here, what I did is I solved for x. Kind of like here, I would solve for dx because my original equation has dx. So dx is equal to du over 2. So when you're dealing with the arcsecant or this form of it, not only do you have to solve for dx, but you usually have to solve for x because it's probably not going to be exactly equal to the derivative, or it's not going to be exactly equal to 2x. If it was 2x, I could just put u in directly, but in this case it's just equal to x, so I solve for x. And then you make the substitutions. So you're going to factor out the 12. So if you haven't done the substitutions yet, go ahead and stick in the substitutions now as I have laid them out. Yeah, you probably still need to leave the absolute value sign. I think you could cancel out the 2's to simplify, but I don't think you still need to leave the absolute value on the x. So there you go. Did I do something wrong? Oh, here? Well, see what happens is this 2 here multiplies by 1/2 from there, so it disappears. So this 2 cancels out with that 2. Is that? It turns out I've done a few of these problems, and it always seems to happen that way, but you don't want to just ignore it. You have to still cancel it out. So because you'll see that anytime, whatever this coefficient is in front of u, you're going to get a half, you're going to get a whatever this value is, you're going to get in the denominator, and whatever you have here, you're going to get in the denominator, but one's being divided. So we're dividing by 1. We're dividing by 1/2, and we're dividing by 2, so that's the same as those cancel out. So you don't end up with the now let's say we're just going to modify this slightly. We're going to put in limits. So we're going to do the same problem, so we're not going to rework the whole thing. So let's say we put in these limits. And so where is that going to show up? Well, for one thing, we're going to have to redefine the limits. So if you have, let me just insert a page here. If this were a definite integral, you'd have one additional step, which would say when x equals 3, u equals 2x. So u would be equal to 2 times 3, which would be 6. And when x equals 6, u is going to be equal to 2 times 6, which is 12. So if you had a definite integral, when you got to this point on the next page here, you would have 12 times the integral from 6 to 12 of all this stuff here, all that stuff. And when you got to the end, you'd have 12 times 1 over 4, so I'm going to this point, times the arc secant of the absolute value of u over 4, evaluated between 6 and 12. So I wouldn't, at this point, I would substitute a in, because that's nothing to do with the limits. That's just to do with the coefficient in front of it has to do with this thing, the a squared part, the a part. But then I would evaluate it here. So I'd have the arc secant of the absolute value of 12, which would be just 12 divided by 4, which is 3. And then I would subtract the arc secant of 6 over 4. But remember, I can't do the arc secant, so I'd have to take the arc cosine of 1 over. So it would be the arc cosine of 4 divided by 12, and you subtract the arc cosine of 4 divided by 6. So hopefully I didn't leave out too many steps there, but that's how you would, if you had a definite integral involving some of these arc trig functions, you proceed, you have the additional step of redefining the limits, but you don't have to plug u back in because we've redefined our limits in terms of u instead of in terms of x. Now you could keep the limits and then you change the limits back and put it back in terms of x, but it really wouldn't save you any time. So might as well just keep it in terms of u. Okay, so that's that one. Let's look at the next one. So this one is really just completing the square to rewrite the denominator. So this is when we have, again, we'd look at this, 13 divided by the square root of 11 minus 8x minus x squared, and you might first think, well, let me let u be what's in the parentheses. And that works most of the time in the past, but now it doesn't anymore, because the derivative of that term in the square root is going to be negative 8 times or minus 2x, which is nothing's in the numerator that fits that. So then you think, okay, the next thing that looks sort of like that is one of the arc trig functions. And there's three options. There's a squared minus u squared. There's a squared plus u squared. Well, it's the square root of a squared minus u squared. There's a squared plus u squared, and there's u times the square root of u squared minus a squared. So they're all very different. Two of them have square roots. If it doesn't have a square root, then it's the arctangent. They have to be added together. So it shouldn't be too hard to figure out which one of those three it fits. So it's going to fit into the a squared minus u squared category. So all we have to do, or all you have to do, because you're going to do it, is to take that term in the denominator that's in the square root and complete the square with a negative leading coefficient. So remember from yesterday, so here it is. Remember what you did, what I did, was you factor out a negative sign to make it positive, the negative's positive. So it's instead of negative x squared minus 8x, it's x squared plus 8x. And then you complete the square inside the parenthesis, but then you, instead of adding the number, or instead of subtracting to balance it out, you're going to add the number. So go ahead and complete the square. And then once you've got the completed square, then you're going to have your constant will be a squared, and the term that you have, the complete square will be u squared. Well, it'll be u in the parentheses, at least squared. And I don't think it's going to be a nice perfect square, so I'll give you some practice on that as well. Let me wonder. So I have a, what do I call it? Popular culture question for you guys. So who cares about, who gives a, well, I was going to say a flip. Who cares about the whole royal wedding thing of Harry and Meghan? She's the only one. You're the only one that cares. Yeah. Okay. It's funny. We were talking to Jennifer this weekend, and we said, "Hey, we're going to be in England when the wedding is," and she said, "Well, I think Americans are more interested than English people." And I'm thinking, not in Allegheny County, because the only person I thought of was Margaret. That she would be the only one that really would follow it at all. So completing the square, you take half of 8, which is 4, square it, which is 16. You add that, but we're really subtracting it, so we need to add it again. So 16 minus 16 is 0. So these two added together become 27. And then you have minus this thing as a complete square, which is x plus 4 quantity squared. So the original integral, I'd factor out the 13, and you'd have 1 divided by the square root of 27 minus x plus 4 squared dx. And then, u squared equals x plus 4 squared, a squared equals 27. U equals x plus 4, a equals the square root of 27, du equals dx. So if you haven't finished it, just plug it in the formula, which is the integral of 1 over the square root of a squared minus u squared du is equal to the arc sine of u over a. I don't think I haven't posted the review for the last test, but I'm going to do that today. I've got my computer, my new computer is acting weird. It's getting bogged down downloading something. So I brought it into school because my home network goes to a crawl, whereas here it doesn't. I'm trying to upload the latest. It can't get the latest updates for Windows. And I think it's because it can't get the latest updates that it's slow. Have anybody had that problem where your computer just kind of, the Wi-Fi speeds just go like, I might only have DSL, so 2.5 whatever it is, megabits is the fastest mine goes, but it's okay for what I use it for. But it's, I don't know why it did this a couple of months ago with the other computer. I had to reformat the whole, start all over again, and I really haven't figured out what it is. It's just annoying. Okay, so here's the answer. 13, it's going to be 13 times the arc sine of x plus 4 divided by the square root of 27 plus c. So you get 13, the integral, the integral of 1 over the square root of a squared minus u squared du is equal to the arc sine of u over a plus c. So u is x plus 4, a is the square root of 27, and if you finished with that, that's fine. Again, you can get the square root out of the denominator. So you'd have the square root of 27 times x plus 4 divided by 27 plus c. Okay, so you guys can hang on to this because we'll probably work some problems on Friday, some more complicated ones. So that's it for today. But yeah, by the end of the day, we'll have the review up, probably before the end of the day, probably by noon. The reason I brought my computer, I used my computer to take the old review and just put it into a format for YouTube. So hopefully it'll be running. It runs fine without the internet. It's just the internet's all